Paralleling neutral conductors in electrical wiring systems is an atypical practice. The primary motivation behind such a design is often to mitigate voltage drop on the neutral conductor, particularly when dealing with harmonic currents produced by electronic equipment. Harmonic currents are non-sinusoidal currents that can introduce complications into electrical systems. These currents can lead to overheating of neutral conductors, cause unwanted tripping of circuit breakers, and contribute to other system malfunctions. By using multiple neutral conductors in parallel, the overall impedance of the neutral pathway is reduced. This lowered impedance minimizes the voltage drop experienced along the neutral conductor, thereby mitigating potential issues caused by harmonic currents. However, paralleling neutral conductors introduces certain risks. Should one of the neutral conductors become damaged or disconnected, it can create a potentially hazardous situation. To mitigate these risks, it is crucial to select appropriately sized conductors and ensure that all connections are made with proper technique and hardware to maintain secure and reliable electrical contact. An alternative approach involves running 3 separate 2-wire circuits to each equipment grouping. This configuration is often more cost-effective and avoids the potential safety hazards associated with paralleling neutral conductors. It is recommended to communicate with the professional engineer to understand the specific reasons for their design choice. They might have specific concerns or considerations that are not immediately apparent. Voltage drop is a critical factor in electrical system design, especially in long circuits or those with high current loads. Excessive voltage drop can lead to inefficient operation of equipment, overheating of conductors, and even equipment malfunction. The National Electrical Code, or NEC, provides guidelines for minimizing voltage drop in branch circuits and feeders. For branch circuits, the NEC recommends a maximum voltage drop of 3% and a maximum combined voltage drop of 5% for both branch circuits and feeders. The NEC provides formulas and tables to calculate voltage drop based on conductor size, length of the circuit, and the current load. These calculations help ensure that the selected conductors are adequate to maintain voltage drop within acceptable limits. Harmonic currents are a significant concern in modern electrical systems due to the proliferation of electronic devices. These currents are multiples of the fundamental frequency, which is typically 60 Hz in the United States. Common sources of harmonic currents include computers, electronic ballasts, variable frequency drives, and other nonlinear loads. Harmonic currents can cause a variety of problems, including overheating of transformers, neutral conductors, and other electrical equipment, as well as distortion of the voltage waveform, which can affect the performance of sensitive electronic devices. To mitigate the effects of harmonic currents, various techniques can be employed, such as using harmonic filters, K-rated transformers, and properly sized neutral conductors. The NEC provides guidance on sizing neutral conductors to accommodate harmonic currents. Grounding is another essential aspect of electrical safety. A properly grounded electrical system provides a low impedance path for fault currents to return to the source, which helps to trip circuit breakers or fuses and prevent electrical shock hazards. The NEC specifies the requirements for grounding electrical systems, including the size and type of grounding conductors, as well as the methods for connecting grounding electrodes. Equipment grounding conductors, often referred to as EGC, are used to ground non-current carrying metal parts of electrical equipment, such as enclosures and conduit. These conductors provide a path for fault currents to flow back to the source, which helps to trip circuit breakers or fuses and prevent electrical shock hazards. The NEC requires that equipment grounding conductors be sized according to the size of the overcurrent protective device protecting the circuit. Bonding is the process of connecting all non-current carrying metal parts of an electrical system together to create a continuous electrical path. This helps to ensure that all metal parts are at the same potential, which reduces the risk of electrical shock. The NEC specifies the requirements for bonding electrical systems, including the methods for connecting bonding jumpers and the types of bonding connectors that are permitted. Overcurrent protection is a critical safety feature in electrical systems. Overcurrent protective devices, such as circuit breakers and fuses, are designed to interrupt the flow of current in the event of an overload or short circuit. This helps to prevent damage to equipment and reduce the risk of fire. The NEC specifies the requirements for overcurrent protection, including the size and type of overcurrent protective devices that are required for different types of circuits. Arc flash is a dangerous phenomenon that could occur in electrical systems. An arc flash is a type of electrical explosion that can release tremendous amounts of energy, causing severe burns, blindness, and even death. To protect workers from arc flash hazards, the NEC requires that employers conduct arc flash hazard assessments and provide employees with appropriate personal protective equipment, or PPE. Electrical safety is paramount in all electrical work. It is crucial to follow all applicable codes and standards such as the NEC and to use safe work practices. Only qualified and trained individuals should perform electrical work. Always energize circuits before working on them, and use appropriate personal protective equipment, or PPE, such as gloves, safety glasses, and arc-rated clothing. Regular inspections and maintenance of electrical systems are essential for ensuring their continued safety and reliability. These inspections should be performed by qualified personnel and should include a thorough examination of all components, including wiring, connections, overcurrent protective devices, and grounding systems. Any deficiencies or potential hazards should be addressed promptly to prevent accidents and ensure the safe operation of the electrical system. In the specific scenario of wiring an office space with multiple computer workstations, several factors should be considered to ensure a safe and reliable electrical system. Firstly, the load requirements of the computer workstations and associated equipment should be carefully assessed to determine the appropriate number and size of branch circuits. This assessment should take into account the continuous and non-continuous loads, as well as any potential future expansion. Secondly, the potential for harmonic currents generated by the computer workstation should be evaluated. If significant harmonic currents are anticipated, appropriate measures should be taken to mitigate their effects, such as using harmonic filters or K-rated transformers. Thirdly, the grounding system should be designed to provide a low impedance path for fault currents, which helps to protect against electrical shock hazards. This may involve using a dedicated equipment grounding conductor for each branch circuit, as well as ensuring that all metal parts of the electrical system are properly bonded. Fourthly, the wiring method should comply with all applicable codes and standards, such as the NEC. This includes using appropriate conductor sizes, insulation types, and conduit or cable types for the specific application. Fifthly, the overcurrent protection should be carefully selected to protect against overloads and short circuits. This may involve using circuit breakers or fuses with appropriate ampacity and interrupting ratings. Sixthly, the voltage drop should be minimized to ensure efficient operation of the equipment. This may involve using larger conductor sizes or running separate branch circuits for each workstation. Seventhly, regular inspections and maintenance should be performed to ensure the continued safety and reliability of the electrical system. This includes checking for loose connections, damaged wiring, and other potential hazards. In addition to these technical considerations, it is also important to communicate effectively with the professional engineer and other stakeholders involved in the project. This helps to ensure that everyone is on the same page and that the electrical system is designed and installed in accordance with the project requirements and applicable codes and standards. The NEC provides detailed requirements for wiring methods, including the types of conductors, cables, and raceways that are permitted for different applications. It also specifies the minimum size and type of conductors that are required for different types of circuits. The NEC also includes requirements for the installation of electrical equipment such as lighting fixtures, receptacles, and appliances. These requirements are designed to ensure that the equipment is installed safely and in accordance with the manufacturer's instructions. The NEC is updated every 3 years, so it is important to stay up to date on the latest changes. The NEC is a complex document, so it is often helpful to consult with a qualified electrical inspector or engineer to ensure that all electrical work complies with the code. In summary, paralleling neutral conductors is an uncommon practice that is typically employed to mitigate voltage drop and harmonic current issues. While it can be effective in certain situations, it also introduces potential safety risks. It is crucial to carefully evaluate the load requirements, harmonic current potential, grounding system, wiring methods, overcurrent protection, and voltage drop to ensure a safe and reliable electrical system. Effective communication with the professional engineer and other stakeholders is also essential. Regular inspections and maintenance are critical for maintaining the safety and reliability of the electrical system over time. Always prioritize electrical safety and follow all applicable codes and standards. When dealing with harmonic current, consider using harmonic filters, K-rated transformers, and properly sized neutral conductors. Ensure that the grounding system provides a low impedance path for fault currents. Use appropriate wiring methods and overcurrent protection. Minimize voltage drop to ensure efficient operation of equipment. Perform regular inspections and maintenance to identify and address potential hazards. By following these guidelines, you can help to ensure a safe and reliable electrical system for the office space. The specific design choices made by the professional engineer should be carefully considered and discussed to ensure that they are appropriate for the specific application and comply with all applicable codes and standards. Remember that electrical work should only be performed by qualified and trained individuals. Always energize circuits before working on them and use appropriate personal protective equipment, or PPE. Staying informed about the latest changes to the NEC and other relevant codes and standards is essential for ensuring that all electrical work is performed safely and in compliance with the law. Ultimately, the goal is to create an electrical system that is safe, reliable, and efficient, and that meets the needs of the occupants of the office space. This requires a thorough understanding of electrical principles, as well as careful planning, design, and installation. By working collaboratively with the professional engineer and other stakeholders, you can help to achieve this goal.